Hello and welcome to the week 11 Math 2419 review. In this session we'll be going over change of variables to polar for double integrals, then we'll get into improper integrals, and lastly we'll start with sequences and some power series. So let's go ahead and get started with some change of variables to polar. This is actually going to be a fairly brief section since a lot of the concepts were covered in last week's double integrals review. So let's say we have a double integral over some region R, and we'll call it a function f of x, y, and we're integrating with respect to both variables. Well, sometimes it's easier to put this region R in terms of polar coordinates. For example, if we had a region that was circular, give me just a minute, I'm going to finish out writing out this formula. Perfect. So let's say we're given a region R that's just the unit circle. So a circle of radius 1 about the origin. If we wanted to integrate with rectangular coordinates, well, we would need to describe this region in terms of x and y, which would give us a pretty not great looking integral of, we could describe it as like the integral from -1 to +1, and the integral from negative square root 1 minus x squared, positive square root 1 minus x squared, where these y values on the top half would be root 1 minus x squared, and on the bottom half it would be negative root 1 minus x squared. But that's not a very fun looking integral. But in polar coordinates, if we describe that same region, it would look something like, well, we just have a constant radius, r is equal to 1, and if we're integrating along this whole disk, the minimum radius would be r is equal to 0. And then we would start with a theta value of 0, and then we would traverse all the way around the circle, giving us an ending value of theta is equal to 2 pi. So you could describe this same region using the integral from 0 to 2 pi, integral from 0 to 1. Then that would be dr theta. And this region is a whole lot simpler. We have just constants in our region, in our limits of integration, so maybe we would want to do that. Well, we can change a rectangular region of integration into a polar one by using this formula. Take your function, and wherever you see an x, you replace it with an r cosine theta. As you do, you simply convert your f of x, y into polar coordinates by using these familiar equations that you learned earlier. And the important bit is you have to include an r. There's an extra r in here. The reason why has to do with some calculus that's a bit beyond the scope of Math 2419, so I won't get into it. But this r is very important. You have to convert your function to polar and then multiply by an r, and then you would integrate normally. So let's go ahead and do an example. Let's say you wanted to find the volume of a cylinder with a height of 2 and a radius of 3. Well, we know that volume can be thought of as the area under a function. In this case, our function is just going to be the height of our cylinder. So z is equal to 2, or you could think of it as f of x, y. Well, if we convert this to polar, it stays exactly the same, since we don't have any variables. And because it's a cylinder, we know that we'll actually be traversing our whole will be going around a full rotation. We also know the radius it's given, that would be 3, so we'll be integrating from 0 to 3. Well, we convert our function f of xy to polar, 2, and then because we converted it to polar, we multiply by an r. Now we have dr d theta. And now we can simply integrate normally, 2 pi. Then we have r squared from 0 to 3 d theta, which gives us the integral from 0 to 2 pi of 9 d theta, which comes out to be 18 pi. And of course, we can check this using our volume of a cylinder equation, which comes, and our volume of a cylinder, if you recall, is pi times the radius squared times the height. And in this case, that would be pi squared times 2, which gives us 18 pi. So this integration is correct. So it's fairly straightforward. The only trick is make sure you're remembering to multiply by that r. All right, that's really it for change of variables to polar. You might see some more complicated problems, but I would rather spend the time going over improper integrals because these be a bit of a different concept. So some integrals, what I mean by weird parts, things that maybe we don't know how to deal with when we're integrating. For example, if I wanted to find, I'll just sketch a graph. Let's say we just took the graph of something like this. I wanted to find the area from here to the right. So everything in this region right here. Well, if I wrote the limits of integration, that would look something like the integral from, if this is 1, that would go all the way up to infinity. And we can't necessarily just plug infinity in as a limit. So this is one example of an improper integral. I'll just note that down here. One of your limits is plus or minus infinity. And I say 1, but really I mean like 1 or more, so it could be both. And we probably wouldn't see that with this function, but one classic example of a function that has 2 infinite limits is actually really important in probability. And that's the standard normal distribution, which looks something like this. And if you're familiar with probability at all, you might be able to recognize that like the probability of some event occurring is often the integral from one point to another. So we could take like everything to the left of this line or everything between these two lines to get a probability of something. But the integral from negative infinity to positive infinity of this probability distribution should be equal to 1. But that is a classic example of an improper integral. But there are some other improper integrals that don't involve infinite limits. Infinite limits of integration, that is. They do technically still involve infinity, though. So let's say I wanted to, just reusing this function from the first one, we'll actually draw out a bit more. Let's say I wanted to integrate from -1 up to +1. Well, that would give me basically this area right here. And here we actually see we have a vertical asymptote. And that's another thing that can make an integral improper, a vertical asymptote. So note that if either of these things happen, or both, you will have an improper integral. And the way we actually solve these is similar regardless of what kind of improper integral it is. We basically rewrite our problem spot, so that maybe the spot that causes the integral to be improper, as a limit. So for example, this first problem, our problem spot is having this limit of integration as infinity. We could rewrite this as the limit as b goes to infinity, integral from 1 up to b. And the second integral, our problem spot is this 0 vertical asymptote. And this one we would actually have to break up into two limits. Like so. We would have the integral from -1 up to 0, which would give us this lower portion, and then the integral from 0 up to +1, which would give us this upper portion. And you'll notice that I actually elected to make my limits one-sided, because for this lower portion, we're only concerned with the negative side of 0, basically. So let's go ahead and do a couple of more concrete examples. Let's say we had the integral from 0 up to infinity of x squared dx. This is a pretty simple, straightforward example. But in this case, our problem spot is the infinite limit. So we would need to rewrite that using a limit statement. The limit as b goes to infinity, integral from 0 up to b x squared dx. And now we simply evaluate this normally. We keep our limit statement, but when we actually evaluate our integral, we get 1/3 x cubed from 0 up to b, which of course gives us the limit as b goes to b. We keep our limit statement, zero, so I'm not going to write that, and then we can simply evaluate this limit. As b goes to infinity, say that this integral diverges, which is basically what we say when it goes to infinity or negative infinity or something like that, if we don't get a real number as our answer. Another quick example. Let's say we had the integral from 0 to 2 of 1 over x. Well, in this case, our problem isn't necessarily either of our limits of integration, since those are both real numbers. At this graph, you'll notice there's actually a vertical asymptote where x is equal to 1. So we actually need to split this integral into two around our vertical asymptote. Like so, limit as a goes to 1 from the negative side, plus the limit as a goes to 1 from the positive side, integral from a to 2 of 1 over x minus 1 dx. Now, of course, we're going to keep our limit statements. Then we would have the natural log of the absolute value of x minus 1 evaluated from 0 up to a. The limit as a goes to 1 from the positive side of that very same function, actually. This time evaluated from a up to 2. And when we actually evaluate these limits, first off, we would get the limit as a goes to 1 of the natural log of 1 minus 1 evaluates to the natural log of 0. And the natural log of 0 is actually negative infinity. So here we have an infinity in our answer. And actually, that is enough to stop. because if you kept working this out, you would actually get like a positive infinity from this term. And one common misconception is you think you can cancel these limits out, but that is not true. If you get any infinity from any part of your limit of your integral, that is enough to say that your integral diverges. So let me repeat that. You cannot cancel infinities. It feels like you should be able to, but you cannot do it. Do not do it. Okay. All right. Now let's do one more improper integral. Let's say you have the integral from not 0, but from 1 up to infinity, this time of 1 over x. Well, our problem spot is going to be that infinity in our limit statement. We do have a vertical asymptote at x is equal to, so we don't actually have to worry about that. First off, we're going to rewrite it using a limit statement. And this would be a convergent improper integral. We can say that it converges to 1. All right. Cool. Let's go ahead and do a couple of practice problems. So work these ones on your own, and then we'll go over them. Start with the 0 to pi tangent of So here's a couple of practice problems. Looks like I was disconnected for a second, but giving fairly simple integrals like e to the x because I want you to focus mostly just on getting the improper integrals and the limit statements correct. So I'll give you a couple minutes to work on those. All right, let's go ahead and go over these. So for question 1, recall tangent of x actually has a vertical asymptote at x is 2 pi over 2. So that's going to be our problem spot for that. So we need to rewrite this as 2 integrals. And I'm going to go ahead and split it up into sine of x over cosine of x, because that's how we integrate tangent. And we would have a second limit as a goes to pi over 2 on the positive side, integral from a up to pi, again, of sine x over cosine of x. And then once we actually integrate, we would get the limit as a goes to pi over 2 on the negative side. We would have a cosine of x as our u, and just simply use u substitution. Cu is equal to cosine of x, du is equal to minus sine of x. So this integral actually becomes the integral of negative du over u, which is of course negative natural log of u. So this would give us negative natural log of the absolute value of cosine x from 0 up to a. But here I'm actually going to say I don't really care about this second integral anymore, because I can see that if I actually plug in pi over 2, or take the limit as a goes to pi over 2, that would give me the negative natural log of cosine of pi over 2. Cosine of pi over 2 is 0, so we would have negative natural log of 0, which actually gives us an infinity in our answer. And just to show that I've left some stuff out, I'll put plus dot dot dot, but that is equivalent to the limit as a goes to pi over 2, and the negative side of negative natural log of cosine of a. That's once again some other stuff. I'm just ignoring the 0 term, because the important bit is once I take this limit, I would get the limit as cosine goes to 0, which is the limit as natural log goes to 0, which gives me negative infinity. Flip it gives me positive infinity. And because infinities don't cancel, that is enough to say that this is divergent. Cool. All right, let's take a look at this second improper integral. There's the problem spot, that negative infinity. E dx does not have any vertical asymptotes, so we don't have to worry about that. So let's go ahead and rewrite this. We have the limit as a goes to negative infinity, integral from a up to 2, e to the x dx is of course equal to the limit as a goes to negative infinity of e to the x from a up to 2, which is e to the second plus the limit as a goes to negative infinity of e to the a. And the limit as a goes to negative infinity of e to the a is 0. So we get a final answer of e squared. So this improper integral converges to e squared. Really straightforward enough. One last thing about notation. Let's say you had an improper integral from negative infinity up to positive infinity. Well, in this case, you don't technically want to write it like the limit as a goes to infinity, limit as b goes to a goes to negative infinity and b goes to positive infinity, integral from a to b. This is considered bad form, so we typically don't like you to do this. Instead, what you're supposed to do is split it up into 2 integrals. And you can pick some any arbitrary. And split it up so you only have to write one limit at a time, like this. So this is the same, it's kind of saying the same thing, it's just mathematically proper. And some professors might take off points if you do this top thing, so I would just avoid it. This is the right way to do it. All right, but that's probably enough of improper integrals. You get the idea. Just a quick recap. Look for the two things that can make an integral improper. Those are having infinite limits or having a vertical asymptote within the region of integration. All right, let's go ahead and move on to sequences. Which are pretty straightforward. In really mathematical terms, a sequence is technically a function. And it is a function that takes integers as input. So, for example, we could have a sequence a sub n is equal to 2n. Well, then it would give out a1 is equal to 2, a2 is equal to 4, a3 6, and so on. But basically, the only thing we're allowed to put in it is integers. And we usually refer to the integers as the positive integers. So the numbers 1, 2, 3, 4, and so on are what you'll usually see used for sequences. But other than that, it behaves just like a function. There is some slightly different notation. Rather than saying like f of x, we usually like to say a sub n. But they're analogous in that this n value is your input, so it's kind of similar to your x, and then you can just plug it into your whatever definition you get in order to get your output. So for example, with this a sub 3, 3 is my input, so to get 6, I just did 2 times my input 3, and that gave me 6. And what you'll see is that a lot of the rules you can apply for functions actually apply to sequences as well. And we'll actually talk about some of those properties when we talk about limits of sequences. So the limit of a sequence, L, we can define to be the limit just as n goes to infinity of some sequence a sub n. And again, this is pretty similar to functions. We can say like that the limit of a function would just be like the limit as x goes to infinity of f of x. And it's evaluated really in basically the same way. If you think back to top-heavy, bottom-heavy, and balanced functions, all those rules still apply. So if we had a sub n equal to like n squared plus n over 3n squared minus 1, well, this is a balanced function, so we could say that the limit would just be the coefficients of the largest terms, n squared on top and bottom. And that would be 1 over 3. So all the same rules kind of apply. So let's say we have this limit L is equal to the limit of the sequence a sub n, and if we have another value k, and this is just going to help us set up some other rules for limits of a sequence. If we have a second sequence and it has a limit of k, well then we can say that the limit as n goes to infinity of a sub n plus b sub n, well that's naturally just the sum of their limits. And if we multiply them, that would of course get us the product. Things do get a bit weirder if your limits are 0 or infinity. If you get indeterminate forms, again, that's going to get it's going to get a bit different, but in general, this is a good rule to know. And of course, if we just multiply any of our sequence by some constant, well, that multiplies the limit by that same constant as well. And we also have the squeeze theorem for limits. Not for limits, sorry, for sequences. So let's say that we have two sequences and they have the same limit. And let's say we also know that we have some third sequence that is always bigger than our first sequence A sub n and always smaller than our second sequence C sub n. Well, then we know that the limit of E sub n has to be equal to that same limit of A sub n and B sub n. And I'm just cleaning this up a bit. So, same principle of Squeer's theorem. Basically, if one of your functions is if one of your sequences, let me clarify, is always between two of your other sequences, and those two other sequences head towards the same value, well, that middle sequence is also heading towards that same value. You can think of it as being squeezed between the other two limits, and that's where we get the name squeeze theorem. But that's all basically the same as with functions. So that should be mostly review for you guys. Now we'll talk about some things that maybe weren't talked about much when you're going over functions, and that's the idea of monotonic. And a monotonic sequence is a sequence that is always increasing or it can also be always decreasing. And the way we express that mathematically is we could say that the current term a sub n is always less than or equal to the next largest term. Or we could also say that the current term is always bigger than or equal to the next largest term. So that's the definition of monotonic. It just means always increasing or always decreasing. And what that looks like is basically you'd have to always be going up. You could never have a negative slope per se. Let's see. Next, we have the concept of bounded above. And we could say that a sequence a sub n is bounded above. Basically, if we can find a number, where we can say this number that we found is bigger than every term in a sequence. And if we wanted to express that more mathematically, we could say something like this. Basically, our number that we picked, our so-called upper bound, is bigger than every term in our sequence. And we could also change that to bounded below if we have an n that is always smaller than every term in our sequence. Finally, we say that the sequence is bounded just bounded, not above or below, A sequence is bounded if it is bounded above and below. Now, this is just kind of a bunch of definitions, so maybe let's take a look at some examples. A bounded and monotonic sequence. Let's say we have a sub n being defined as 2n over 3n squared plus 1. And n always has to be bigger than or equal to 1. Well, in order to show that it's monotonic, first off, I'm going to make a guess as to whether this is increasing or decreasing. Because my denominator is a higher order, it has an n squared term versus just an n term, I'm going to guess that it's decreasing because bottom-heavy functions tend to decrease. So I'm going to guess that this is monotonic decreasing. What that means is that my current term should be bigger than or equal to my next biggest term. Well, in order to show that, I need to find out what my next biggest term is in terms of n plus 1, in terms of n. So I simply plug in an n plus 1 wherever I see an n, and that gets me 2n plus 2 over 3n squared plus 6n plus 4 as my a sub n plus 1. And then I simply plug this into my inequality. A sub n is bigger than or equal to a sub n plus 1. Now, in order to actually prove this, I need to simplify it down a bit. So I can cross multiply, and I get that 2n times 3n squared plus 6n plus 4 is bigger than or equal to 2n plus 2 times 3n squared plus 1. Now, if I keep on simplifying, I get 6n cubed plus 12n squared plus 8n is bigger than or equal to 6n cubed plus 6n squared plus 2n plus 2. And when I cancel things that are common on each side, that cancels the 6n cubed. I can simplify things down to the statement 6n squared plus 6n is bigger than or equal to 2. And I know that this is true because I specified at the very beginning the sequence is only valid where n is bigger than or equal to 1. And from here, it's pretty straightforward. Because this 2 is constant and n is always positive, well, my lowest value of n would be 6 plus 6 gives me 12 when n is equal to 1. So clearly 12 is bigger than 2. So we can say that this is monotonic decreasing. And it all started out with this statement here, this inequality that came from our definition of being monotonic decreasing. Every current term is bigger than the next term. All right, next we need to show that it's bounded. So first off, clearly, if we just say there's no negatives in this sequence, so clearly we can say because n is always positive, we can just go ahead and pick a lower bound of 0. Now we need to find an upper bound. Well, We also know that our sequence is monotonic decreasing. Well, what that tells us is every term is smaller than the one that came before it. So that means that our largest term should be our first one. And simply by plugging in 1 for n, we get that our largest term would be 2 times 1 over 3 times 1 squared plus 1, which gives us 2 over 4, which is 1/2. So 1/2 is actually our biggest term in our sequence. So we can actually say that 1/2 is an upper bound. And if you're a bit confused by why I said that 1/2 is an upper bound, let me just draw a quick picture. So I know that my function is always decreasing. So if I take the first term at 1 right there, well, if I wanted to start drawing my function, even if I didn't know anything except for that it was decreasing, I would have to go down a bit. Well, it's still decreasing, so I have to go down a bit. And at any point that I decide to stop, I still have to keep going downward because I know that it's always decreasing. I can't ever turn back upwards. That kind of implies that this very first term, wherever we started, has to be our largest term, and we can say this is our upper bound. Every term in our sequence has to be below this line or equal to this line, so we can say that that is an upper bound. And there is a theorem that says a bounded monotonic sequence must converge. And when we say converge, that means that its limit exists. So for example, if we had the sequence a sub n is -1 to the n, well, this isn't technically monotonic, so its limit does not exist. But if we had the sequence a sub n is equal to just 1 over n, well then, this actually is monotonic and bounded, and its limit is 0. We could say that it converges to 0. This is a helpful theorem in some situations, so I just thought I'd note it down. We'll go ahead and give you a practice problem. Should be a C. Practice. Show that the sequence a sub n is equal to 1 over 2 to the n, where n is bigger than or equal to 1, is monotonic and bounded. And I will give you a minute or two to work on that. All right, let's go ahead and go over this problem. So, in order to show that it's monotonic, you need to show, I'm going to assume this is monotonic decreasing, because I can see that the limit is 0. So, I need to show that each current term is bigger than or equal to the next biggest term. Well, a sub n is 1 over 2 to the n. A sub n plus 1 would be 1 over 2 to the n plus 1, which is 1/2 times 1 over 2 to the n. And if I wrote this inequality, replacing a sub n with the actual sequence definition, well, there's that. And if I simply subtract 1/2 times 1 over 2 to the n from each side, well, then I get the inequality 1/2 times 1 over 2 to the n is bigger than or equal to 0, which is of course true. And that tells us that this sequence is monotonic decreasing. And once again, you can clearly see that this sequence is bounded below by 0 because it's always going to be positive. So we can just say that our lower bound is 0. And because, again, it's monotonic decreasing, that tells us that our upper bound is going to be our first term. And our first term is 1 over 2 to the first, which is 1/2 once again, is our upper bound. There we go. So because we found a lower bound and an upper bound, our sequence is bounded. And we already showed that it's monotonic decreasing, so we are done. All right. Sequences are fairly straightforward. You can do a lot of the same things to them that you can to functions, so if you keep that in mind, you'll probably be all right. Now, lastly, we'll start talking about what's called often power series or just series, and something called convergence. So we'll start off with what a series is. And to put it simply, it's the sum total, sum of all the terms in a sequence. So if we had a sequence a sub n, it was a sub 1, a sub 2, a sub 3, and so on, well, we could write that the series is the sum a1 plus a2 plus a3 plus every term in this series. And you'll frequently see it denoted using this sigma notation, which is just a sum. We put our starting term here. If our sequence starts at 1, we would have a 1 there, and we would go up to infinity because our sequence is infinite. And usually it's pretty hard to find the exact sum of a series. It's not impossible, especially depending on the form of your series. So there are certain types of series where you can find the exact sum. A lot of the time, we're actually concerned not with the exact sum, but whether or not this sum is even like a real number. So we can say that if this sum is a real number, then we say that the series converges. But sometimes the sum might not be a real number. It could be positive or negative infinity or something like that. Then we say that our series diverges. And two really basic examples of a convergent series and a divergent series are, let's say if we took the really simple series that said that every term was just 1. Well, the series would be the sum, not infinity. I'm going to specify that n is bigger than or equal to 0 of a sub n. Well, we could write that out as just 1 plus 1 plus 1 plus so on forever. Well, clearly, if you take a 1 and add it up infinite amount of times, you'll get infinity. So this is a simple series that diverges. And if we wanted a simple series that converges, we could just take the series that says every term is 0. And once again, I'm just going to start with n being 0. Well, if you take 0 and add it to itself infinitely many times, no matter how many times you do it, sorry, that should not be an infinity, you should still end up with a 0. So because that's a real number, we say that it converges. And both of these series are pretty dang simple, so not a whole lot going on with those, but they're good for illustrating the concepts of convergence versus divergence. Now, there are some tools we can use to determine whether a series converges or diverges. And we'll start by introducing the first to you today. And this is known as the Nth Term Test. And basically it says, if you have a series, n is equal to 0, summed to infinity, of some sequence a sub n, if the limit as n goes to infinity of your sequence a sub n is not equal to 0, well then your series diverges. Basically, if these terms, when they get very large, aren't basically 0, then you have a problem and it's going to diverge. Think about it with the earlier series we had where we're just adding ones. These ones didn't approach 0, and because we were adding a significant amount on every time, that means that we had to keep getting larger and larger, and eventually we just diverged. So our terms have to go to 0. One thing to note is the nth term test cannot tell you if a series converges. So let's say you take the limit as n goes to infinity of your sequence and you get it's 0. Okay, cool. That does not mean that your series converges. It simply means that more work is needed to determine if your series converges. So let's go ahead and do 2 quick examples using the nth term test, and then we'll call it done. Our first example is going to be this fairly simple series. Well, a sub n is equal to n, and we know that the limit as n goes to infinity of n, well, that actually is infinity. And infinity is not equal to 0, and because that's not equal to 0, we would say that our series diverges by the nth term test. Let's do another example. Well, here our sequence is the n goes to infinity of 1 over n is 1 over infinity, which is 0. Well, because we got a 0, we can't necessarily make a conclusion. So we'd have to say the nth term test is inconclusive. And as it turns out, this power series is actually divergent, using some other tests that will be introduced to you later on in the course. But big thing to note is you cannot apply the nth term test to say that a series converges. Do not ever do that. But that's just about all that I've got for this week. So thanks for coming and have a nice day.